Warm greetings and wishes, friends and dear students. Today, we are going to see about the determination of the slope and deflection for a given cantilever beam of span L, which is fixed at one end and free at the other end. The fixed end I call it as capital A and the free end I call it as capital B. And it carries a constant load of capital W at the free end. And the beam is of span L. Using double integration method, what will be the slope and deflection at the free end of the cantilever beam, so which is having a point load at the free end. Now, the famous equation for finding the slope and deflection, the case of double integration method is EI d square y by dx squared is equal to the moment. The moment at the free end from the cantilever is minus w into x, because at the right hand side of the section, at any section xx from the right hand, the clockwise moment is negative, so minus wx. So this is the equation of EI d square y by dx square is equal to minus wx. Then EI d square y by dx square is equal to minus wx. Once you integrate this moment equation, EI dy by dx is equal to minus ws square by 2 plus c1, where c1 is the constant of integration. Once again, we have to integrate the slope equation. You will get EI into y, where y is the deflection at any required point on the beam, is equal to minus w into s cube by 3 into 2 plus c1x plus c2. So this is the deflection equation we have to use by substituting the corresponding value of x, either at the free end x is equal to 0, or at middle x is equal to L by 2, or at the fixed end when x is equal to L, to find the slope and deflection. So where c1, c2 is called as the constant of integration. So this constant of integration can be determined by using the boundary conditions. The two boundary conditions we are going to use as when x is equal to L, that is from the free end to fixed end, that is at point A. When x is equal to L, both slope dy by dx and deflection y are 0. So first I am using the condition when x is equal to L, you put it in the slope equation, you will get the constant C, you will get the constant C2 as, that is C1 as WL square by 2. Then using the deflection equation, what you have seen before, we can get the C2 value. So when x is equal to L, you substitute in the deflection equation, the C2 value will be coming out as minus WL by 3, where W is the load applied at the free end, L is the span of the beam, and EA is the flexural rigidity of the beam. Here EA is constant from one end to other end of the beam, it is from A to B. After the calculation of the integration constant C1, C2, you substitute in the general slope and deflection equation. Finally, you will get the value of the required slope and deflection at the free end. So when x is equal to 0, that is at the free end B, because I have taken section xx from the free end, you substitute when x is equal to 0, the slope dy by dx at b, that is theta b, we are getting as minus WL square by 2EI. Then you substitute when x is equal to L. Again, the deflection is 0. When x is equal to L, both slope and deflection 0. That's why we have put x is equal to L. You determine the slope, that is theta b is equal to minus WL square by 2EI. After the substitution of x is equal to 0, you will get the corresponding deflection. If you are substituting the corresponding value of x equal to 0 in the required deflection equation, the value will be working it as minus W L cube by 3EI, where E is the flexural rigidity of the beam, which is constant for the entire beam span, and L is the span of the beam, and W is the applied concentrated load at the free end. So this is how we have to find the slope and deflection equation for a given cantilever beam with the span L and point load at the free end. So you are getting the maximum deflection at the free end. YB is equal to minus WL cube by 3EI. Minus indicates the downward deflection. Then you are finding the slope at the free end, that is when x is equal to 0. You are getting WL square by 2EI. So this is how we can proceed for the point load at any distance from the free end, that is at a distance of x or L by 2. We can calculate. Similarly, you can calculate for UDL, etc. So in the next video lecture, we can solve the numerical problem on the simply supported beam and cantilever beam which carries a point load or UDL. Thank you very much for patient listening. God bless. வாழ்க வையகம், வாழ்க வளமுடன்.